So with that, it's my pleasure to introduce Dr. Michael Anderson, who is the California State Climatologist for the Department of Water Resources. He joined the Division of Flood Management in the forecasting section in 2005, and that's where the State Climatologist position is housed. He took the current position full-time in 2008. Mike is kind of local talent. He got his PhD and his master's both from UC Davis in civil environmental engineering. He has an extensive background in hydroclimate systems modeling and monitoring. So I've been trying to lighten the mood a little bit. So when I engage the speakers, I ask them for some sort of amusing or interesting anecdote to set the seminar off on a nice note. So Mike gave me one that was very befitting of the general theme of his talk, that, you know, in California we're 1 or 2 storms away from being in a drought or being in a flood. So he said that also, you know, as a professional climatologist, he's interested in storm chasing. So last year he took a trip to Vancouver Island to go storm chasing, and it just so happened that the week he arrived, he found the Pacific calm and glassy, while we had our one atmospheric river event here in California. So I said here, perhaps next time, Mike, you should plan a staycation. So with that, please join me in welcoming Mike Anderson.
There we go. Now we're cooking. All right, so here we are, Climate, Drought, and Change, with a nice picture of Oroville Reservoir from 2009. Those of you who like a little more up-to-date version, there's Folsom in January of this year. You'll notice something distinctly lacking in both images. Anyway, so we'll start off today with where we are with our current drought conditions, and I actually had time this morning to populate this with the hydrology update from today. So current is an appropriate word there. Then we'll talk of this relative to our 20th century droughts, tap into a little bit of decadal scale variability, and finish off with some signs of change. And preface everything from the beginning, we start that California's topography is one of the drivers of our weather and climate. All those fantastic mountains get in the way of moisture flowing into the state from the Pacific Ocean, and that creates our rainfall. And our rainfall, this image modulated from one that Marty Ralph uses, shows phenomena that impact atmospheric river events that help California. And atmospheric river events are important to California both for water supply and for flooding. And it shows just a whole bunch of processes going on in the Pacific Ocean that need to line up in a particular way. And when they line up in just the right way, we can have a flood. But from a drought perspective, you can look at all the number of ways things can miss. And it doesn't take too many misses in a 90-day window where we get half our annual precip for things to fall apart, and we end up where we're at. All righty, so one of the main things you can look at of this, all the nice, pretty colors on the image here are water vapor. The reds, oranges, and purples are very high concentrations of water vapor. Yellows, greens, a little lower blue is dry air. So that's the moisture element. Then we need wind and a storm system to run into that plume of moisture, and that gives us our heavy precip. All right, here is from December 27th, 2013. This is the new extreme precipitation monitoring network that we installed over the last 5 years. And what these little numbers on the map are showing is the amount of water vapor that's in the air over California. So this is if you took all the water from the surface all the way to space, condensed it out, that's how many centimeters of water would be there. And this is in December, one of our wettest months. And you'll see for Sacramento, there was all of half a centimeter of moisture. If you're up in Yosemite, you had half a millimeter. It's not going to rain when things are this dry. If you don't have moisture, we're not going to get our rain. Now, we'll contrast this with the week before I ran off to Canada. and we had a little moisture come in. Now we're over 3 centimeters. So now we're cooking. Anything over 2.5 centimeters, which is about an inch of moisture, you can really go start getting some precip out. And remember that most of the moisture in the atmosphere is in the first 10,000 feet. So it's coming off the ocean. First 10,000 feet, it runs into what in California? It runs into mountains. And so then you get combined convergence and lift, and that benefits our precip. You can see, though, down there in the deserts, not as much, and get up into Oregon, not as much. These are fairly narrow bands of moisture. So, again, you're talking the whole Pacific coast of the U.S., and you want it to target a very small space, our space. And so here we are. So here is a way to see what falls out with CDEC product called the 8-Station Index. Those are your 8 stations from Mount Shasta City down to Pacific House, where most of our water supply originates. This is a precipitation index, nice average of 50 inches. And we see our wettest year there at the top, 88.5 in an El Nino year, 82, 83. And we see one of the driest years down there in 76, 77. Had a little blast in September there that knocked it off from 23, 24 being the driest, but both those are pretty miserable years. Fun thing about 76, 77, it's an El Nino year. So now when people tell you it's going to be an El Nino year, you know that it's been the driest in the last 60 years, it's been the wettest in the last 60 years. So you should have some good information there. All righty, so now we can look and we see we have some other in there. We see the other green line that has more of a step function type to it, and this is 2012 and 2013. And you'll see the first step right here. This is at the end of November, beginning of December. Now, this just so happened that this was when we announced the Extreme Precipitation Network at the American Geophysical Union meeting in San Francisco. Little did we know we'd have an atmospheric river event soaking all the participants of the meeting. We had high water in the Russian River, and you can see at the time that we passed 82, 83. We were on track for being wetter than the wettest year on record. And there we are again. So then here we get around Christmas, and we get another blast, and we're above again. And we're thinking to ourselves, this is great. Oh, by the way, we picked up a third of our water year precip in this event on the 8-Station Index. And in this blast, which not as much, we got a third of our snowpack in the northern Sierra on that blast. What could go wrong? Well, look at the next 14 months. As we trace along here, and not much happens. And we start into this year, not much happening. And look what happened by the beginning of February. Whoops, let's go back up. You have crossed the entire distribution of historical water years in California in a 14-month period. So you went from wetter than the wettest, and after 14 months of absolutely nothing happening, now we're drier than the driest, and things are looking a little uncomfortable. I run off to Canada. Lo and behold, that causes it to rain because I brought my in-laws into town. Worked very nicely, got us above the driest there. Then we had a nice, run in February and March. It got us up. Boy, this thing likes to move. Got us up there at 29.7, where we are today. So you can see then that those atmospheric rivers are important elements of our precipitation. Now you notice this one that got us out of the worst. That's about 8 inches in 2 weeks. This was about 14 inches in 8 days. So there is a difference to them and what size you get, but we still need them to get the supply we need. Now here we are now looking at a 5-station index in the San Joaquin Basin. Now here you'll notice 2012, 2013's in purple, and so you see that big step at the beginning of December didn't get as far in terms of getting up to the wettest end of the distribution, and it still goes flat as well, and it stays flat into the royal blue line there that digs under the driest year. But you'll see that down here has been drier than what's up in the Sierra. So tail of this drought is the north, as bad as it is still doing better than as you head south. All right, tailless snowpack, and these are going to be a bunch of lines that you're going to really strain your eyes to see if you want to look on this, so I will suggest maybe downloading the presentation and looking at this at a later time. But you see, way back a few years ago, we were ice skating at Tenaya Lake, and people were saying, oh, it's dry, but then late season snowpack comes in the north at least, and we get up to average. That takes care of everything, right? Got an average snowpack, we're good. Well, in the central and south, you'll see it didn't quite measure up. They only got 50%. And for then the next 2 years, hanging out at that about 50%. But you do 3 years at only a 50% snowpack, and remember 100% snowpack does not equal 100% runoff, and you've got dry conditions interceding. And our largest reservoir that we rely on for our water supply is not quite holding up. Mother Nature didn't deliver. All right, here's a different way to look at it. This is from NASA doing a nice product here. This is from MODIS. And folks at JPL are doing an experimental product of taking the MODIS data and creating a model that gives you an estimate of snow water equivalent in that image. The image on the right, the one on your right is an elevation band. The one on the left that says May 4th is the model average of 13 years of what SWE should look like for May 4th. The blues are about a meter of SWE. There's May 4th of this year, as you can see, and then the week before. And you can see, particularly in the Feather Basin, there isn't a whole lot of snow showing up. You see that one funny little spot on the American River, a little wetter than most. That one big storm that did blow through, there was the bullseye. That was the high terrain that actually got the snow out of it. So as you can see, we can rock back and forth a little bit there. The high elevations are in the Tuolumne. Still got a little bit, but not nearly what you'd want for this time of year. All right, so I have a friend in D.C. who likes California. He thinks California is a fascinating state to dig through its data. So he took the summary data of 154 reservoirs, and he went through CDEC, the text products, and grabbed each month's percent average since 2010, and he plotted it relative to average. And so you can see there, what we'll really focus on here is in 2012. We had that, whoops. All righty, so we had beginning of January, big storms were well above average, 120%. Doing great, but things are dry, it comes down. April, May, get our snowpack kick. Then we start trailing down. 2012, we end up below average. Fall kicks in, we get a little bit. 2013, and look at the dive in 2013. When you go extremely dry and you had been wet, and remember that right before we spent 14 months with almost nothing happening, we were rivaling our wettest year. So you get into December, you're rivaling your wettest year. What are your expectations for your water supply and environmental needs that you're going to think, we're all set for runoff, right? Well, if it doesn't happen, you're going to borrow storage to do it, and thus we did. And we get into 2014, and you see it still tailing down. As a percent of average, you can still say, though, for as awful as it's been, we're still faring better than we did back in '77. On CDEC, we do this kind of plot, updated daily. If you like to look at it, it's a nice little chart. The red line is average. The blue is where the water is. You have the blue number at the bottom is percent of capacity. The red is percent of average for that date. And then we can drill into this a little further, and we get these kind of plots. This is Shasta Reservoir, and you can see then here in 2012-13 is that black line, and it's above the light blue, which says, hey, we're above average, and until we start delivering water, and then we dig down into our storage. As I said, we come in, We're digging down. We don't quite get to 77 before then. The snowmelt kicks in, and then we're digging down. And currently, as of midnight last night, we have a little less than 1.4 million acre-feet in Shasta. And for this time of year, you'd like it to be over 2.5. Here's a story of Oroville, somewhat similar. But look, when we dug down, what did we manage to do? We dug under that 77 line, and we dug under it for quite a little ways until the spring melt and those winter, February, March storms kicked in to help out. And we're above, and we're still sticking above, but now we're down to 1.18 million acre-feet, and we want to, again, be above 2.25. So we've got a lot of, what I say, this is a lot of incidental flood space storage. It's always a bright side, isn't there? All right, now here's the fun part. Remember I said the American River watershed was a bullseye for that one event. Look at there at the beginning of February, of this year. They're digging down, they're digging deep, well below the 77 line. Look what happens in a week. Boom, 100,000 acre-feet of storage comes in. And that takes an absolutely miserable situation and says, all right, better than we were? Definitely helpful. And then as it comes in, and then you see again tailing down, and you can see relative to the other years and lines. All right, now here's San Luis. This is a little tougher story here. So we see the line in 2012, the black one is kind of hanging out with the driest year. And then heading into this year, well under it almost the whole year. Towards June, finally snuck above the worst year. So then now you get to ask yourself, well, okay, where's the new worst year? There's possibly a new line to add to the chart. All righty, so that's where we are. And here's a nice picture of Lake Oroville. And houseboats getting a lot closer and friendlier. And some exposed lake bottom there. So a little context. So this is data from NOAA's Climate Division data sets, and the Climate Division 2 is the Sacramento River Basin. All the little blue diamonds on there are each year's average temperature for the year and the annual precipitation, and it starts back in 1895, and all the blue diamonds go up to the year 2000. Big triangle in there, the yellow one, that is the period of record average. All the black squares are the 21st century. When I look at this, it seems to me we're sampling preferentially in the distribution on a particular side. Then you get, and this is calendar year data, so this is a little different than how water managers normally look at the world. It's a different perspective to offer here. We'll look at 2013. We found a new part of the distribution that hadn't been mapped before. And people tell you, well, this is the worst drought since 76, 77. 76 was the previous low point on that chart in terms of precip. But look at the difference in this year. It's 2 degrees warmer. So there's additional challenges to be had 40 years later. Story isn't different when you move into the San Joaquin Basin. Same depiction of characters there between 1895 to 2000, 21st century and period of record. Again, 2013, warmer and drier than anything that had been seen in the 100 years previous. And the 21st century is sampling distinctly on one side of the distribution. In this case, we did actually find one year that could find it to the other side of the period of record mean. And statewide, same story again. So calendar year 2013 was definitely one that you could say we hadn't seen before. All righty, so now we'll take you from even a different perspective. We whip around here. Try not to give ourselves whiplash. So this is a 36-month accumulation statewide Climate Division data, but this time we're parsing it by precip year, so July 1st to June 30th. And 81 to 84, which includes that 82-83 El Nino year, was our wettest one there. 94 0.78 inches of precipitation in this data set. 74 to 77 used to be the lowest when we totaled 46.65. Average should be close to 70 for that 3-year accumulation. And then we look at the past 3 years, and we're down to 45.19. So from this perspective, over that 3-year period, we've plumbed a new low in our precipitation with the Climate Division data set at NOAA. Alrighty, so yet a different way to look at this. A-station index cumulative deviation. So with this one, I took the short fall from average each year. As long as the year before was below average, appended that year onto the previous year's shortage. So you see these big, long 6-year droughts. There we are. So 29 to 34. Right there, pardon me. More recent one, whoop. More recent one there, and we have the 76, 77, where, you know, in 2 years you really dig deep. 24, single driest year, really quickly there. And then this one, whoops, wow, we're really rolling here. There you go, a little preview. So then you see how this year matches up from that perspective. And as it says, it assumes no further precipitation this year. Well, unless something really interesting happens in September, which it did in 77, we'll call that good. So just a bunch of rankings. This year is the 8th driest water year at that 29 inches. So while it's low, we've got a lot of friends down there. However, in the 5-station index, it's down to the 3rd driest. So you're really starting to dig deep there. For the 8-river index, in terms of runoff from the 8 rivers in the Central Valley, we're the 4th driest. For that 3-year amount, it's 3rd driest. There's another product from Western Region Climate Center called the California Climate Tracker, which we'll see a little bit later. For it, it breaks things up into different regions, and for its Sierra region, which spans from the Feather Basin down to the Kern, it is the 2nd warmest water year to date, and it has had the warmest winter for that region. Alrighty, so we'll talk on sequencing as we transition then into that notion of decadal scale variability. So 20th century, we see 2, 3, 4, and 6-year droughts. So certainly we're not anything out of the unusual yet. The multi-decadal dry period from 1910 to 1940, where you're looking at over that long period, your average in that time period is a good 20% less than the period of record average. So that makes things a little more challenging to manage too if Mother Nature on average for quite an extended period of time isn't delivering. But then the paleo record, multiple 10-plus years drought, as well as the Stein century-long dry periods, we'll call those climate shifts at that point. And the reason we bring that up is one of the outcomes of this year's drought was refining the Paleohydrology Study for the Sacramento, San Joaquin, and Klamath Basins, done by University of Arizona gang. The data and report are available on the department's webpage. There is the address to there, and we'll take a quick look. So here's a nice little poster that got made for it. And we can see the Klamath River's tucked way up there where hardly anything interesting happens, so I say. Sacramento Basin, we see this kind of wiggliness in these long periods where things kind of go dry. And San Joaquin and then the Colorado River. And we see kind of those decadal scale wiggles. And those are what we're going to kind of look for and dig into here for a little bit here. So anyway, that's San Luis Reservoir from this year. As we dig into temporal variability. Well, let's start with year to year. We win, so to speak. California's interannual variability is greater than anywhere else in the continental U.S. You'll see everywhere east of the Mississippi River, their standard deviation relative to their mean annual precip is between 10 and 20%. One year looks an awful lot like the next. So from the perspective of all the folks back in Washington, D.C., one year looks like the next. Where do you suppose they get most of their cases where that notion completely falls apart? That might be us, where down here in the deserts where your mean's kind of small, you can find your year-to-year variations being 70% of the mean. But notice even when we're up here on the north coast, try not to advance the slide here, we're up in the greens, here where remember your mean is 120 inches of precipitation, and you still have a variability that's 40% of that. That's just downright jaw-dropping. Anyway, we can say we do things differently out here. All right, so here's a whole bunch of different data sets with 10-year moving average put through it. And entertainingly enough, the same pattern kept falling out. And this was, I did this actually for a talk in the Russian River watershed. And so we have LA County down there at the bottom, just to show Southern California, because some of these patterns extend across the state. The other four are the 8-station and 5-station index, and then Sonoma County and Mendocino County. And it's fascinating that the two counties that sit right on top of each other have patterns and magnitudes that are very similar to the 8-station and 5-station index. But you see, even the little wiggles line up really well. And some interesting work going on at Scripps is looking at, again, getting back to the atmospheric river, the frequency of those events relative to this decadal scale variability, and using that as the explaining that variability. Alrighty, so let's dig into the 8-station index and some of the entertaining things that have been happening with it. Again, we see the year-to-year big swings, and if you stare at it long and hard enough, you might convince yourself you see kind of a decadal scale oscillations in there. Read that yellow line at the bottom there. 9 of the last 14 years have been below average. Remember what I said about 1910 to 1940, where Mother Nature wasn't exactly giving a full deck. 21st century so far hasn't quite been the same. And in fact, if you break it down and you look, the period to record average 50 inches from 1971 to 2000, so closing out 20th century, that average was 53 inches. We were rolling. We had a lot of big years. Things were doing really well. Also, I had the biggest year and also the lowest year in the last 60. But then we hit the 21st century in those 14 years, and it's not quite up to that period of record average. And you see the monthly breakdown, and you see that December, you see that huge spike. But note at the bottom that both 2012 and 2014, you had the 3rd and 4th driest Decembers in 90 or so years of record. Now, how can you have a big spike in 14 years of average when you're including some of the bottom feeders there in the past 3? You have some really, really wet Decembers where you have over 20 inches that kind of skew those statistics a bit. Go to the runoff in the Sacramento River, and we see, again, the period of record average, not quite 18 million acre-feet, almost 19 million from 71 to 2000, but you get into the 21st century, you're down with 16 million acre-feet. Okay, so if 18 is the long-term average, you're down 2 million acre-feet from that, but if you're trying to deal with how you're managing things to close out the 20th century, you're working with 3 million loss. It's a bit of a trick to do. Now, it's like I said, things got dry as you head south. Now here, 10 of the last 14 years on the 5-station index were below average. And as you see here, again, closing out the 20th century, things were a little wetter than the period of record average, but the 21st century has definitely so far been shorter on that. And again, 2012 and 2014, we had the tied with the driest when no precip fell in December of 2011. And 10th driest with only 1.1 inches. Now, if you're looking at the period of record average in December of over 6 inches and the 10th driest is only an inch, there can be some really dry years down there in the San Joaquin, offset by some really big years. Again, getting back to the notion of atmospheric rivers being really important to how things shape out for us. Now here we see the runoff in the San Joaquin Basin, and it's an entirely different shape to the hydrograph because the mountains tall enough down there, things are driven by snowmelt. But we see that period of record, a little below 6 million acre-feet, 71 to 2000, a little above 6 million acre-feet. 21st century, only 5.3 million acre-feet of runoff. So again, we've got 14 years here now where we're working with a deck that isn't fully loaded, so to speak. And that always brings to question, I tell you what, this first time it goes dry, is this climate change? What percentage of this drought can you apportion to climate change? I remember what I said in the climate division data. We're sampling distinctly on one side of the distribution. We're sampling on the warm side of the distribution. Things that historically were at the edge, we're now giving them a lot of friends to work with. And those that were left of the period of record average, we don't seem to get back there anymore. Alrighty, so then we hear expectations. Well, there's smaller snowpack, more rain, less snow, earlier snowmelt onset, more variability, and more extremes. And then the next question that pops up, are we seeing these already? Well, yes. How you define them and how they manifest themselves and how it consistently behaves over years and years, not just one oddity year, because remember, year to year, we have the most crazy variability. And this is the fun thing when people talk about trends. Well, does your trend show up? Do you know how big a trend has to be to show up with that kind of variability? That'd be a little scary. So we have to kind of tease things out a little more. And one way that an effort colleagues up at Western Region Climate Center kind of set out to try and tease this out is through the California Climate Tracker. If you Google California Climate Tracker, it'll take you to the website, give you an opportunity to dig in, and this is all based off the National Weather Service Cooperative Observer data set, going back to 1895. And all the different shapes there in the state, those are the different regions that they did a statistical analysis and figured out which co-op stations were statistically representative of the same region. And what you see here for precipitation for water year to date 2014, if you see red, that means it's never been drier. If you see orange, that means you're in the top 10. And if you see yellow, that means you're still below average, but not doing as bad. Now remember, we had a pretty good monsoon here for the Colorado River Desert. But even that didn't quite bail things out. You look at temperature, both maximum and minimum, you're seeing a lot of red, particularly along the coast, particularly where you have a lot of California's population. Particularly in those maximum temperatures. And about the only place that isn't cooking, so to speak, is up on the north coast where things are a bit cooler, but still not below average. They're still either average or above. All right, so here then are the time series, and you start to see, particularly on the right with the minimum temperatures, it's getting to where you don't see too many blue lines, which is where the departure is below the 1949 to 2005 average. So we're starting to sample again consistently on one side of the checkpoint. All right, so here's yet another advertisement for a new metric being worked on in the department. Aaron Cuthbertson, Alyssa Lynn, and then Kelly Redmond up at Western Region Climate Center. They want a more rain, less snow metric. How would you go about actually computing that and being able to track it? Well, here's their first shot at it. And so you see the funny little shape cut out of California, and that's the snow melt basins. And they're using some gridded data products for temperature and precipitation to try and tease this out. And this is the mean for that region, which we'll nominally call a state because that's where snow is important, is 72%. And then year to year, you see the difference of that year's ratio of rain and snow. And there are a lot of different elements in a water year that go into whether you're getting more rain or snow, including total amount of precipitation, a big storm that's either wet, warm and wet, or cold. But anyway, it gives you a chance to look at it. And again, it's not as if things are monotonically increasing. Lots of variability to sift through, but you start seeing that you're sampling preferentially. All righty, so let's close this out here. The current drought, along with our other 21st century friends, is we do have some record-setting characteristics, and we are warmer than our 20th century counterparts. And so we're really going to have to start, instead of just saying it hasn't rained as much, you really have to start bringing in temperature as an element to describe how these droughts are evolving. Atmospheric river events are significant inputs into our annual precip totals. We'll definitely see noticeably fewer such events in drought years, and they actually cluster. If you look at the water year outcomes and you see some clustering, and it relates to the number and size of the atmospheric river events that do make their way through. So it may seem odd that studying the wet extremes can help inform you on the dry side as well. Expectation of increased variability. Well, new extremes and extreme transitions. Well, 2013 is going to be a pretty good example, where we started at the wettest end, and by the time we get into 2014, we're on drier than driest. All right, so how do you plan for dealing with this? Well, don't think just because the future may not be reflective of the past that you have to abandon everything you've seen in the past. We have a lot of variability. There's a lot of elements in there that are not necessarily just right there waiting for you. You got to do a little digging, but there's a lot of good information there, and you can also dig into the paleo data sets that the department has been putting together. And I said the trick here is to increase your understanding of causal mechanisms and watershed condition response. What happens when the watershed is wet and something happens as it dries out, and then when it is dry, how much effort does it take to wet it back up to where you're getting runoff that you can refill the reservoirs? And with that, we'll call it good. And there's my email address. If you have any questions, you feel like sending me a note, please feel free to do so. Oh, and one last other thing I'll do is another closing commercial. I don't have too many of them here, but the California-Nevada Applications Program, which is a regional integrated science assessment center of NOAA, is located at, well, it's actually a partnership between Scripps Institute of Oceanography and Western Region Climate Center. They put together a little 4-pager describing the current drought and different aspects of it, including some of the topics I touched upon here today. You can download it from their website. For those of you that want to take it with you, the first 10 customers that race up and knock each other down to grab one can get one.
What is their website?
Oh, hopefully they put it on here. If not, I'll have to tell them that was one of the things we missed. Yeah, we did. No, there it is. It is cnap.ucsd.edu.
Any questions?
Okay, you mentioned the comparison between 20th, 21st climate, and we're kind of warmer this century. For 20th wise, how far back in years are you making this comparison? How far back data do we have accurately that you can make that comparison?
Well, for this particular one, I just went back to the 76-77 drought, which was the last time we dug down to that part of the distribution. And there had been a lot of comments of, wow, this is the driest we've been since that time period. And it's like, well, yes, that's true, but there is a difference in that we're also warmer. And so that effort was really more just to kind of bring that into the conversation based off of that comment specifically.
And so what do we know about the warmer temperatures' effect on atmospheric rivers?
Fantastic question. Because a warmer atmosphere can hold more water. Part we're still working on is digging through history, finding proxy measurements. Like I said, we have a new network to directly observe these, but it's only 5 years old. not a whole lot of data to go on from that. We're looking at proxies we can get from the historic record and look through and see which elements of them are getting bigger, say more water vapor flux, change in the duration of the event, which may lead to a bigger storm, but if you don't get enough storms or you start from a drier condition, maybe if you do get one storm, you get a better bang for your one event. We're still digging into it.
Does the state have developed a model, predictive model yet for future precipitation we might see based on the various factors that affect our climate?
Not yet. I mean, we have different models being developed to try and be able to forecast atmospheric river events, but that's more on a 2-week time scale than if you're trying to look at elements of it, how it might project into future climates. We are, as I said, trying to find proxies that you can look at, one, that are well represented historically, and then look at the change of those. We've been doing work the past few years on that particular topic, and this work should be finishing up here pretty soon.
You mentioned that there's quite a bit of variability in how wet the ground is from prior rainfall. When the ground is very dry, as I imagine it's become now, is it more likely to absorb more water or to flood more water?
It depends on the soil. It's never easy. There are some soils, actually from that February event, we had some measurements in the Russian River watershed, and 60% of the precip from that event went into the soil moisture storage. So it didn't even show up as runoff. So a huge deficit in that particular basin, but there may be other soils that when you hit them with heavy precip, they become almost hydrophobic, which may generate more runoff. So another element to kind of dig into and figure out where you may have some vulnerability in heavy precip events.
I'll ask one. Where you're talking about these rollouts of these different data collection systems and monitoring systems, what's the longer term, like what's coming out, or if you had unlimited funds, what would you put in if you could?
Another fantastic question. So what we have with the new network here, we have a dozen sites where we're measuring the freezing elevation in the atmosphere, and this is the height where rain becomes snow. And this is hugely important on the west slope of the Sierra. Tells you how much of the watershed is participating in direct runoff and how much is actually accumulating snow for the seasonal snowpack. And those are located along the foothill region where they get a really strong signal. They kind of get out of the soup of the Central Valley, but are not quite high enough where they get snowed on. And so there's kind of a fine line elevation band where we've been able to locate those. We also have, as you saw, the GPS MET. Now, that's a fun one because that starts with the GPS sensors that the Plate Boundary Observatory put in to track tectonic movement. Well, it turns out you can put some meteorological instrumentation on there. It improves their signal, so they get a better signal, and some of the noise they're removing turns out to be the amount of water vapor that's in the atmosphere. And so there we found a fantastic partnership that little collaborative effort, we're each getting good information out of it. Also interesting, from that same network, a paper came out last week saying that that same monitoring network could be used to refine some of the estimates of the GRACE satellite system in terms of the total amount of water within a watershed footprint. Right now, GRACE is only sensitive enough to tell you like a Central Valley wide, and they're saying with the GPS you could actually get a better shot at getting a watershed scale estimate of that. And then one of the other elements we have is soil moisture, which is kind of spotty, but again, and this has been the ongoing discussion. I have a point measurement of soil moisture, trying to understand what that means in a broader watershed condition is a bit of a trick, and we've been working with the USGS on exactly that problem, and coming up with some metrics to monitor that actually give you a better translation to a landscape scale, and then so we'll be pursuing that. So yeah, with unlimited funding, definitely dig more into that. The other ones that are really nice but kind of pricey are along the coast. We have 4 sites where we're setting up what we call atmospheric river observatories, and this is actually to quantify the flux of water vapor. So you get winds and water vapor coming ashore. And we'll have one of those at Eureka, Bodega Bay, Point Sur, and Goleta. The Navy had been running one on San Nicolas Island, but sequestration closed that down. So maybe when things get better, we can talk to them about reopening it to give us something for Southern California and get a 5th point in the network. They're kind of pricey items, but that gives us fantastic information in actually quantifying that flux coming on shore. And once you start measuring it, then you can start tracking for change. And like I said, unlimited budget, it would be nice to maybe get another one of those up in the northern Sacramento Basin. Done some monitoring that shows that as the moisture comes in and you get a Sierra barrier jet that kind of moves then the flow up the valley, there's an exit point in the Bernie Gap, which actually allows that atmospheric river to penetrate then inland. We don't have a way to quantify right now other than the model to say how much is going through that gap and how much is then plowing into the mountains above Shasta Reservoir, and trying to better understand that process and how the barrier jet interacts with that. That's probably next on my list of things that would be fun to try and quantify, because that would probably play a big role in how water enters our state and how much we get out of it. And then on another set, we've been doing some work with NASA on trying to do spatial characterizations of the snowpack. I showed you a MODIS product, which is a model. We're actually trying to do some measurements using LIDAR. And if you want to look that up and follow along with that, that's called the Airborne Snow Observatory. And so far it's been great because NASA is supplying the funding and we're supplying what we'd like them to look at. But as with all NASA projects, they're kind of short term. So trying to translate it into a long-term monitoring may be a bit of a trick.
Any other questions? All right. Well, thanks, Mike. That was fantastic.